Our paper studies the interpretability challenges in the multiclass setting that does not exist in binary classification or regression. We focus on a class of models called the generalized additive models. As an illustrating example, here is an additive model with only one feature and three classes. In this simple example, the prediction is determined by three shape functions, one for each class, as plotted in the figure on the right. The output of the shape functions, FA, FB and FC, are called the logits, and they are passed through a softmax function to give the class probabilities. In this particular example, all three shape functions are linear. In general, they can come from any nonlinear function class. The problem with multi-class models is that different models with distinct shape functions can be equivalent in terms of prediction. This is because adding the same constant to each logit does not change the output of the softmax function. Here are four models with visually distinct shape functions that are all rising, falling and then rising, having jumps in the middle, and oscillating. Surprisingly, however, all of these different models make the same prediction. Because this example only has one feature, we can plot the predicted probability of each class as a function of this feature, as you can see in the right figure. One can see that the probability of class A is increasing, while the probability of class B and C are both decreasing. None of the shape functions on the left reveals this pattern. In this paper, we address this challenge by developing a post-processing technique that transforms all the different but equivalent models to a canonical form, which visually agrees with the model's prediction. The method guarantees that the slope of the shape functions agrees with the model's prediction, and the shape functions are as smooth as possible without avoiding the first property. The challenge described in this paper and the proposed solution also apply to linear models, such as logistic regressions, sparse linear models, and SVM. These simpler models are often used in explaining black box predictions. More details about the paper can be found at this address.